Okay, so the next section, 2.4, is about sequences. Sequences and series. So I want to skip this section because it will be covered, will or was covered in Math 114. But one full chapter in Math 114, Calculus 2, is about sequences and series and convergence of sequence, convergence of series, and the test for convergence and important types of series. So for this reason, I don't want to go into the details again in this course. So let's move on to next section, 2.5, cardinality of sets. So if you remember, we defined cardinality. We said cardinality means number of elements. Well, in the beginning, number of elements looks like a very simple concept. Well, number of elements, if it's finite, we can count them. Is it 5 elements, 10 elements? And if it's infinite, well, we can say it's infinite, the number of elements, like natural numbers or integers. But the important, yes, that's can be said that it's true. But the important job that we want to do here is to compare the infinities. Well, yes, for example, natural numbers and real numbers, both of them have infinitely many elements. But which infinity is bigger? Are they same infinities, same type of infinity, or different type of infinity? So here our main job is to compare infinite sets. Which infinity is bigger than the other? Okay, so let's start with the simple case, which is the finite set, finite case. So definition. The cardinality of a set of the form, let's say 1, 2 to n, and n here a positive integer, denoted by, remember the cardinality, we gave two notations, card or just like an absolute value notation. Is defined as n. Number of elements, cardinality means number of elements, and if you have a set of the for 1 to n, naturally we can define it as n. Now, when can we say that two sets have the same cardinality? So next definition. Next definition, given two sets, A and B, we say that they have the same cardinality and use the notation cardinality of A equals cardinality of B if there exists a bijection F. Bijection in your book, this section also calls it a one-to-one correspondence. Correspondence F from A to B. So another name for bijection is one-to-one correspondence. If there exists a bijection, or also called one-to-one correspondence, between two sets, then we say that those two sets have the same cardinality, and the notation we use is cardinality A equals cardinality B. So for example, let A equals, let's say 1, 2, 3, 4. B equals, let's say 10, 13, 91, 235. Then cardinality of A is equal to cardinality of B. But you could tell me, well, it's obvious that because both these element sets have 4 elements, so the cardinality have to be equal. But yeah, it looks obvious, but how would you justify using the definition? Remember that in mathematics, we have to always use the definition. Even if something looks obvious, we still have to use the definition. Definition says two sets are called to have same cardinality if there exists a bijection from one set to another. So if you want to show that these two sets have equal cardinality, you have to construct a bijection from one set to another. So let me say consider so you can write here, show that, and then this is the solution. Consider F from, let's say, A to B. And how would you define it? So F of 1 equals 10. F of 2 we can define as 13. F of 3 we can define 91. F of 4, 235. Then this F is one-to-one and onto, and hence a bijection. So what does that mean? So thus, you can conclude that the cardinality of 1, 2, 3, 4 is same as cardinality of the other set, 10, 13, 91, 235. And this means that the cardinality of this set, 10, 13, 91, 235, is equal to 4, right? Because if you remember, the very first definition we provided in this section was that the cardinality of the set 1 to n is defined as n. Now here we have a set 1 to 4. So the cardinality is defined as 4. And you also showed that cardinality of 1 to 4 and the other set are equal. Why? Because we constructed a function which is one-to-one and onto from one set to another. Right? Look at this function. It's one-to-one because any two different inputs have different outputs. And it's also onto because why? Because every element in codomain occurs as an output. The first element in codomain is 10, occurs as an output, 13 as an output, 91 as an output, 235 also as an output. So the function is one-to-one and onto, and therefore bijection. Therefore, the cardinality of these two sets are equal. But cardinality of left-hand side by definition is 4. So cardinality of right-hand side is also 4. So this type of reasoning that we said for a set with 4 elements can be repeated for any set with n elements. So there was nothing special about this 4. With 5 elements, you can provide a similar argument with 6 elements as well, and so on. So let me leave as exercise that show that the cardinality of, A1, A2, AN is equal to N for any A1, A2 to AN belong to R, and any positive integer N. So as long as you have a positive integer N and any N real numbers, A1 to AN, the cardinality of that set is N. The reasoning is very similar to what we just gave for 4 elements, a set with 4 elements. Okay. Now, the very first surprising result I want to tell you about is, let me call it maybe a proposition, is that cardinality of odd numbers is equal to cardinality of all natural numbers. This is a little bit surprising. If you intuitively want to answer this question, cardinality of only odd numbers is bigger or cardinality of all natural numbers? Well, in some level, both of them are infinity, right? They have infinitely many elements. But how can we compare those types of infinity? Are they same infinity or different infinity? Well, according to the definition that we provided for equality of cardinality of two sets, we'll see that these two types of infinity are actually the same. Why are they the same? Well, we have to look at the definition. When do we say that two sets have the equal cardinality? If we can construct a bijection from one set to another. So if I want to show that the cardinality of these two sets are equal, then I just need to construct a bijection from one set to another. So proof and construction of such a bijection is very easy task. So consider, let's say f from 1, 2, 3 to only odd numbers. F of n, I want to define as 2n minus 1. Then f is 1 to 1. Why is it 1 to 1? Because if I have f of n, let's say equals f of m, that means 2n minus 1 must be equal to 2m minus 1. That means 2n must be equal to 2m. And that means n must be equal to m. Also, f is onto. Why is it onto? Well, how would I show that a function is onto? I have to take an element in the codomain. Codomain here is odd numbers. So take, and let's say n, for example, in the set of codomain. Then n is equal to 2k minus 1 for some integer k. Any odd number can be written of this form for some integer k bigger than or equal to 1, in fact. Any odd number can be written in this form, and that means n has to be equal to f of k. So I showed that any element in codomain is f of some input. That means n must be in the range of f. And that means f is onto. If I show that every element in codomain must be included in the range, well, then that means the function is onto. Well, there you are. So we showed that the set of elements containing odd positive integers have the same cardinality as set of all positive integers. So definition, any set. So this set that, we saw that the cardinality of a set equal cardinality of natural numbers. Cardinality of natural numbers is called aleph naught. So it's a Greek letter I would write for you. Cardinality of natural numbers is called aleph naught. And this is the notation. Okay. And so another part of the definition, any set whose cardinality is the same as cardinality of n, which, as we said, is called aleph naught, is called a denumerable set. So aleph naught is just a notation for cardinality of natural numbers, and any set whose cardinality is same as cardinality of natural numbers is called denumerable. And next definition, a set is called countable if it is either finite or denumerable. So remark here, any finite set can be represented as, let's say, A1 to AN, or can be written in the form, can be written as A1 to AN for some integer n. Similarly, any denumerable set can be written as A1, A2, A3, and conversely, meaning that if elements of a set of a set can be listed as A1, A2, A3, and so on, then that set is denumerable. Okay, so this is the remark. But any finite set, of course, can be written as A1 to AN, and of course, the converse is also true. If you have a set of the form A1 to AN, is of course finite. But what about denumerable sets? Now, the second part of remark says, if you can list the elements of a set, if you can say, okay, this is the first element of the set, this is the second element of the set, this is the third element of the set, then in that case, the set will be denumerable, meaning that it has the same cardinality as n, which is equivalent with saying that there is a bijection from that set to n. So let me give you a proof for this remark, maybe at least one part, and then you can do the rest yourself. Proof of remark. Second part. Let, for example, A be denumerable. We want to show that the elements of A can be listed as A1, A2, and so on. We want to show that in this case, if it's denumerable, we can say that, okay, which one is the first element? There is a first element, there is a second element, and so on. So A is denumerable means what? So assumption here is that A is denumerable. What does that mean? That means cardinality of A is equal to cardinality of natural numbers. Denumerable set means a set whose cardinality is same as natural numbers. Now, if cardinality of two sets are equal, do you remember the definition says what? The definition says that the cardinality of two sets are equal if there is a bijection from one set to another. So A is denumerable, it has same cardinality as N. So that means there exists a bijection. Let's say F from N to A. Bijection because it's one-to-one and onto. So it doesn't matter if you can say from A to N or from N to A. If you have two sets, A and B, if there is a bijection from A to B, there must be also a bijection from B to A as well. You just need to consider inverse of the original function. If F is a bijection from A to B, F inverse is always a bijection from B to A. Okay, so there is a bijection. Now, F of 1, so define A1 to be F of 1, A2 to be F of 2, and so on. Then the elements A1, A2 would be same as F of 1, F of 2, which is same as range of F, right? F of 1, F of 2, and so on, means range of F, set of all outputs of F, but F is on 2, so this is same as A. Because F is on 2. On 2 means what? Means range is same as codomain. Well, there you are. We listed the elements of A in the form A1, A2, and so on. This is what we wanted to show. We want to show elements of A can be listed as A1, A2, and so on. But here we show that A is equal to the set A1, A2, and so on. So that means we listed elements of A as A1, A2, and so on. So I proved one part of this remark. The other parts, let me leave as exercise, other parts. So proof of other parts of remark, exercise. Okay. So we talked about denumerable sets and also countable sets. So denumerable means same cardinality as natural numbers. Countable means either finite or denumerable. And we already saw that the set of, for example, odd positive integers is also denumerable. So what other set do you think is denumerable other than the set of positive odd integers? What other set do you think is denumerable? So another proposition. What about the whole integers? Do you think the whole integers is denumerable? Meaning that the cardinality of z is the same as cardinality of n? Or do you think cardinality of z is bigger than cardinality of n? Again, in the beginning, one may think that cardinality of z should be bigger than cardinality of n, but surprisingly, that's not the case. Cardinality of z is equal to cardinality of n. So cardinality of z is equal to cardinality of n, i.e. z is denumerable. And hence countable as well. Denumerable means we know is always countable because countable means either finite or denumerable. So how can I prove this proposition proof? We need to construct a bijection f, let's say from n to z. Again, when or how do we show that two sets have the same cardinality? If I can construct a bijection from one set to another, bijection means 1 to 1 and on 2, then that means those two sets have the same cardinality. Now I want to construct a bijection here. How can I do that? So n here, by n I mean 1, 2, 3 to z, which is 0, 1, 2, 3, minus 1, minus 2. So if I define, for example, identity function, f of x equals x, well, in that case, it will be 1 to 1, but obviously not onto. Onto means that every element in codomain, every integer in Z must be must occur as an output of F. But it seems that there are too many outputs and just a little input compared to those outputs. How can we solve this issue? Well, the good news is I have infinitely many odd numbers and I have infinitely many even numbers. How about if I try to cover, because Z has three types of integers, positive numbers, negative numbers, and 0. So how about if I try to cover positive numbers with odd integers in n negative numbers with even integers in n, and 0, I can cover it with one of the elements in n. Let's say 1, for example, I can cover 0 with 1, and then cover the rest of z with rest of n. How about that? So f of 0, I'll define f of 1, I'll define as 0. First element of n, let's map it to 0. F of 2, let's say, for example, negative numbers, I define, map them to, it's like even integers, I map them to negative numbers. So f of 2, let's say -1. F of 4, -2. F of 6, -3, and so on. Similarly, f of odd integers, the remaining odd integers, because 1 is already used to cover 0, but I still have the rest of odd integers. So let's say f of 3, I can map it to 1. F of 5, right here. So f of 3, I can map to 1. F of 5, I can map to 2. F of 7, I can map to 3, and so on. So now I just need to come up with a formula for f, and I'm done. So for the even integers, it's obvious. What is the pattern, do you think? So the pattern is f of, let's say, k is minus, right? So there's always minus in the output, minus k over 2, if k is even. For even numbers, like f of 2, we said -1, so -2 over 2. F of 4, -4 over 2. F of 6, -6 over 2, and so on. What about the odd ones? F of k this time. So I can say k -1 over 2 if k is odd. Why is 3 mapped to 1? Well, 3 first, you will subtract 1 from 3. 3 minus 1 is 2. 2 over 2 then is 1. Similarly for 5. Why is it mapped to 2? 5 minus 1 is 4. Then 4 divided by 2 is 2. Then 7. First subtract with 1 again. 7 minus 1 gives you 6. Divided by 2 gives you 3. And so on. So what is f then? So f is from n to z. And then f of k is equal to 0 if k is 1, right? Remember, the first element in the output in the codomain is covered by the first element in the domain. F of 1 is 0. And minus k over 2 if k is even. Remember, 2, 4, 2 goes to -1, 4 goes to -2, and so on. And k minus 1 over 2 if k is odd. K minus 1 over 2. So 1 is 3 minus 1 over 2, or 4. 2 is 5 minus 1 over 2, and so on. So you can check that f defined this way. So check that f is 1 to 1 and onto, and hence a bijection. So once we show that there is a bijection between our two sets, that means that the two sets are have the same cardinality. Therefore, z is denumerable, and also therefore a countable set. Okay, so now the next definition about the inequality for cardinalities. When can we say that one set has less cardinality compared to the other. So definition, given again two sets A and B. We say that cardinality of A is less than equal to cardinality of B if there exists a one-to-one function f from A to B. So if there is a one-to-one function f from A to B, then we say that cardinality of A is less than equal to cardinality of B. We say that cardinality of A is less than cardinality of B if cardinality of A is less than equal to cardinality of B and cardinality of A is not equal to cardinality of B. So it's a similar convention that we have for numbers. When do we say that A is less than B? If A is less than equal to B and A is not equal to B either. So for example, cardinality of 1, 3, 7 is less than equal to cardinality of 1, 5, 10, 12. Again, this looks obvious because the first set has 3 elements, second set has 4 elements. But again, we have to prove using the definition. What does definition tell us to do? Cardinality of A is less than or equal to cardinality of B if you can construct a one-to-one function from A to B. So if you can construct a one-to-one function from A to B, then we say cardinality of A is less than or equal to cardinality of B. But if you can construct a bijection from A to B, then we say that those two sets have equal cardinality. So what is the construct one-to-one function from A to B here? So consider f, let's say from 1, 3, 7 to 1, 5, 10, 12. So f of 1, let me define as 1, f of 3 as 5, and f of 7 as 12. F of 7, let's say as 10. So then this f is one-to-one, and that means cardinality of 1, 3, 7 is less than or equal to cardinality of 1, 5, 10, 12. Okay, and then we also have a theorem. So theorem, Schroeder-Bernstein theorem, Schroeder-Bernstein theorem, given two sets A and B. If cardinality of A is less than or equal to cardinality of B, and cardinality of B is less than or equal to cardinality of A, then cardinality of A is equal to cardinality of B. What does that mean? So i.e., in other words, if I want to translate this into a language of functions, and in other words, if I look at the original definitions, because original definitions of all these concepts were done with functions, whether you can construct a one-to-one function from one to another, or whether you can construct a bijection from one to another. So when you say cardinality of A is less than or equal to cardinality of B, what does that mean? So in other words, if there exists a one-to-one function let's say f from A to B, and if there exists a one-to-one function, let's say g from B to A. Okay, so let me explain to you. This part means if there is a one-to-one function f from A to B. This part means there exists another one-to-one function, maybe we can call it g from B to A. So if we have these two such functions, then there exists a bijection, let's say h from A to B. This is very interesting. If you have two one-to-one functions, one from A to B, one from B to A, then you will have a one-to-one and on two function from A to B. So this new function h may or may not be same as f. Remember, we had a one-to-one function f from A to B, also one-to-one function g from B to A. Now this function h, which is going to be both one-to-one and on-two from A to B, may or may not be same as the original function f. So this is one way. So this theorem suggests one way to prove the two sets have equal cardinality. So one way to prove that two sets have equal cardinality is by showing that the first set has less than equal to cardinality of first set is less than equal to cardinality of second set, and also cardinality of second set is less than equal to cardinality of the first set. Okay, so let's look at an example of this theorem. So example, show that cardinality of open interval 0 to 1 is equal to cardinality of open 0 to 1, open 0, closed 1 interval. So again, we have two infinite sets, open interval 0 to 1, and half open, half closed interval 0 to 1. How can we compare these two infinite sets? Are they same type of infinity, or one of them is larger compared to the other one? So we want to show that these two are equal in cardinalities. So how can I show that two sets are have equal cardinality? Again, if I want to use the original definition, I have to construct a bijection from one to another. You can try doing that. You can try to construct a bijection from, let's say, open interval 0 to 1 to half open, half closed, 0 to 1. And you will see that it's hard to do that, hard to construct a bijection from one set to another. But it will be much easier if we use the previous theorem. Previous theorem, Schroeder-Bernstein theorem, was saying that if cardinality A less than equal to cardinality B and cardinality B less than equal to cardinality A, then they must have equal cardinality. So here, the solution, we will use Schroeder-Bernstein theorem above. So first, showing that cardinality 0 to 1 open is less than equal to cardinality 0 to 1. How can I show this? Remember the definition? One set is has less than equal to cardinality of second set if there exists a one-to-one function from first set to the second set. So I need to construct, to consider a function, let's say f from 0 to 1 open to half open, half closed, and it has to be one-to-one. So which function would you consider that is one-to-one and from open 0 to 1 to half open, half closed? Well, obviously I can consider f of x equals x. It's one-to-one, obviously, identity function. And when the inputs are chosen from open interval 0 to 1, The outputs will be also in open interval 0 to 1. Therefore, they will be also in the half open, half closed as well, right? Because the open interval 0 to 1 is a subset of half open, half closed 0 to 1. Identity function is 1 to 1. That means 0 to 1 is less than or equal to 0 to 1. Next, showing the other way, 0 to 1, half open, half closed, less than or equal to open interval 0 to 1. So this time we can consider, let's say, G from 0 to 1, half open, half closed, to 0 to 1. So what would you consider as your G of X this time? Again, I need a 1-to-1 function. Again, well, the easiest choice would be identity function, but identity function does not work this time. Why? Because if you use identity function, the domain is half open, half closed, right? So that means the inputs can be chosen anything from the domain. Therefore, the input might be 1, number 1. If the input is 1, and you choose the identity function, what will be the output? The output will be also 1. But I am not allowed to have 1 as an output, right? Because the codomain is open interval 0 to 1. Therefore, the range must be also included in the open interval 0 to 1. Remember that the codomain must always contain the range. So if 1 is not in the codomain, it cannot be and is not allowed to be in the range either. But if you use identity function, 1 will be in the range. So identity function is not good enough this time. But how about if I scale everything down, right? Because right now my only problem is that 1 will be, if I choose identity, 1 will be mapped to 1, but I'm not allowed to have that. But what about if I scale everything down? Let's say if I divide everything by 2. So G of X equals X over 2. Then G is obviously 1 to 1, right? X over 2 is a 1-to-1 function. And if X belongs to 0 to 1 in the domain, remember domain is 0 to 1, then G of X will be included in open interval 0 to 1/2 closed interval, which is a subset of 0 to 1. If X is chosen from 0 to 1 closed interval, G of X will be from open 0 half closed at 1/2. But even half open, half closed at 0 to 1/2 is still a subset of open 0 to 1, which is exactly what I needed, right? I needed my range to be a subset of open 0 to 1. So then G is 1 to 1. Thus, what can we say? Thus, we can say that the cardinality of half open, half closed is less than or equal to cardinality of 0 to 1. So now I have 2 inequalities. So let me call this one 2. And let me call this one, let's say 3. So 2 and 3 together, what do they imply? Lastly, 2 and 3 combined with the theorem that we saw if cardinality of A less than equal to cardinality B and cardinality B less than equal to cardinality A, then Schroeder, Bernstein would imply that cardinality of 0 to 1, half open, half closed, is equal to cardinality of open 0 to 1, which is exactly what I needed to show. Okay, guys, so this was an example of Schroeder-Bernstein theorem. So next time we will also look at other countable sets. So far we saw that odd functions, for example, are countable, as the set of all integers is also countable. What about, for example, rational numbers? But surprisingly, we see that even the whole rational numbers is still denumerable. It's still same cardinality of as n, not bigger. So that's one thing we'll see. And also we'll see, so far we haven't showed that there exists any sets which is not denumerable or countable, because every set that we have seen so far was either finite or same cardinality as n. So one question could be, is there a set? Can we say that there exists a set that is not countable or uncountable, in other words? The answer is yes. So for example, this open interval 0 to 1 that we just looked at it. But in this example, of course, we just showed that the cardinality of 0 open interval and half open, half closed are equal. But we did not show whether these cardinalities are same as cardinality of n or are they different. So next time we'll show that the cardinality of this set 0 to 1 is not same as cardinality of n, meaning that it has to be uncountable. So open interval 0 to 1 is uncountable. So this is what we'll show next time. And we'll also look at, as I said, some other countable sets, such as rational numbers. We'll show that the set of rational numbers is also countable. So next time on Thursday, next session on Thursday, we'll have an exam, test number 1. And next lecture, I will upload the next Monday. Okay, guys, thank you and see you on Thursday. I'll send you the link on Zoom and please join there to write the test. Okay, so thank you and see you.